Welcome to lecture 3 of part 2. In this lecture, we introduce multiple linear regression. Simple linear regression models the value of y, the dependent variable, as a function of a single independent or explanatory variable. Multiple linear regression, we actually use more explanatory variables. In this notation here, we have k explanatory variables. The index I refers to the observation. We therefore, in this notation, have n observations. Linear actually refers to that the model is linear in the parameters beta, which means that there can be quadratic forms, for instance, for the values of x. For instance, we can have that xi2 equals xi1 to the square. Or we can even have that xi3 equals xi1 to the power of 3. If that is the case, we refer to multiple linear regression as polynomial regression. As in the case of the simple linear regression, we also need to make assumptions for our model. The assumptions are very similar. We first take the expected value to be equal to 0 over all I, which is equivalent as the equation which we have here. Also, the variance of the error is equal to sigma square. That is also for all I, which is equivalent by stating that the variance of y equals sigma square. Once again, you can note that this variance does not depend on any value of the explanatory variables, which implies then that the variance is constant over all the different values of the explanatory variables x. Also, the covariance between the errors are equal to 0, which then implies that the covariance between any pair of the y values are also equal to 0. We once again assume normality for the error, which then would imply that the yi's are independently normally distributed. We can also, in vector notation, write that the errors follows a normal distribution with an average 0 and a variance sigma square identity matrix of order the number of observations n. We can write the multiple linear regression model in matrix notation. We have that the random vector y equals y1 all the way up to yn, the n observations from the previous slide. We can also write each observation in terms of the multiple regression model. We can introduce a parameter vector beta, and then we can rewrite the matrix expression in this form over here, where we have this vector over here, the error vector, epsilon. So in short notation, we have y equals x beta plus the error epsilon. Note that the matrix X have dimensions n observations by k plus 1 explanatory variables where we have actually an intercept, which make up the +1 over here, plus the k explanatory variables. Also, the rank of X equals k plus 1. The matrix X is known as the design matrix. The assumptions which we've introduced on the previous slide can be also written in this matrix notation way. Here if we introduce these assumptions, we have that Y follows a multivariate normal distribution of dimension n with an expected value x beta. Why the expected value x beta? Well, we have that Y, the expected value of the random vector Y, equals the expected value of x beta plus epsilon. And that equals just x beta because we assume that x is given. And the expected value of epsilon equals 0. Also, as from the previous slide, we saw that the variance should be sigma square indicator matrix of order n. Another way of putting the assumptions is to put them in terms of the error, which implies that we have a multivariate normal with an expected value of 0 and a variance as given. For example, let's consider a multiple linear regression model with two explanatory variables. We have y equals beta naught plus beta 1 x1 plus beta 2 x2, the two explanatory variables x1 and x2 plus an error. We also know from the previous slides that the expected value of the random vector y equals x beta, which is in this case equal to beta naught plus beta 1 x1 plus beta 2 x2. Graphically, we can visualize this as follows. There's the x1 axis, the x2 axis, and there we have the y-axis. Then we see that y is the hyperplane which lives on top of the x1, x2 surface. So for a value over here, a coordinate over here, we have that it projects onto the hyperplane over here, for instance. We have for another coordinate over here that it projects onto the hyperplane over there. And for a coordinate over there, it projects onto the hyperplane over there. The multiple linear regression model can be written in matrix notation. The random vector y equals the design matrix X, the parameters vector beta plus the error vector epsilon. The parameter vector beta equals beta naught, beta 1 up to beta k. We now need to go and derive an estimator for beta. For the vector of parameters, which consist of beta 0, beta 1 up to beta k. We will once again use the least square principle to find the optimum values as estimators for beta. Theorem 7.3.a gives the least square estimator for beta. It states that beta hat equals x prime x inverse x transpose times y. We will prove this on the next slide. We can obtain the error as follows. The error equals y minus x beta. If we replace beta with the estimator for beta, we can get the estimated errors. By taking the inner product of the errors, we get the least square criterion, which we need to minimize to obtain the value for beta hat. So the least square criterion is presented by this equation. By taking the derivative towards beta hat, setting it equal to 0, we can derive that beta hat equals x prime x inverse x prime y. On the previous slide, we show that beta hat is an extreme value for the sum of squares. It actually still remains to show that it actually minimizes the sum of squares. Please work through the proof on the slide by starting off and considering an alternative estimator for beta. Then conclude that it's only possible to have a minimum if b equals beta hat. Next, we derive the expected value of beta hat. Replacing beta hat with its formula, using the fact that x is constant, we can move the expected value into y. Then replacing the expected value of y with its value x beta, we can conclude that the expected value of beta hat equals beta. This implies that beta hat is an unbiased estimator for beta. Please consider the proof of the covariance of beta hat, and that the covariance of beta hat is given by sigma square x prime x inverse. We can also derive the expected value and the covariance of beta hat making use of the assumption of multiple regression. Since beta hat is a pre-multiplication of y with this constant, it follows that beta hat follows a multivariate normal distribution with expected value 0 and covariance given here. The error sum of squares is the sum of yi minus the predicted value for yi squared. It's also given by the inner product, which is equal to the expression over here. This is also equal to y prime times a matrix times y. This matrix is an idempotent matrix, which will be very important in the theorems which will follow next. S squared is equal to the mean square error. The mean square error being defined as the error sum of squares divided by n minus k minus 1. We will see in the next slide that the expected value of S square equals sigma square. Thus, S square is a method of moment estimator for sigma square.